Okay, the lecture today is going to be about the chain rule. I'm going to go ahead and first tell you about this statement of the problem. Then we are just going to go ahead and briefly review what is meant by composition of functions. Then I'll give you the chain rule formula. We are going to work quite a few examples. Then from there I'll hopefully give you a geometrical explanation. And then kind of a simplified proof. And I'm going to leave it to the students who are interested to come and see me in the office hours or read the actual proof of the chain rule on themselves. So the way this is laid out from the more practical and applied point of view toward the more and more abstract point of view, depending on how far of an interest you have on this topic, you can just go as far as you like. Okay, first thing, what is the problem that we want to talk about? Suppose you have a function cosine of something and you want to differentiate that. Well, you have learned about how to differentiate cosine. If I just had y being a cosine of x, then y prime, or in other notation dy dx, that would have been just minus sine of x. We have gone through this and understood what is involved here. Here is the statement of the problem. What if the argument that I was using in cosine wasn't just a simple x, but some other function? So suppose I have y is equal to, say, cosine of just say x squared. What would the derivative be? Or if I had y is equal to, say, sine of x cubed plus x plus 1, what would the derivative be in that case, and so on. So the idea is that if I have one familiar function combined with some other kind of function, and I want to differentiate the result of this composition, what would that be? That's what we are after. The answer is going to be short and simple, but it's going to take a while to get used to it and understand what is really involved. So let me go ahead and just tell you a few words, review the idea of composition of functions for you. Composition of functions. That is what is really happening here. You have one function being combined with another one. Let me just take two functions that are more familiar to you than, say, these trig functions. Here is a nice one, say g of x. I take it to be, let's keep it simple, 2x plus 1. And f of x, let's take it to be, say, x squared plus 3x plus 1. If I want to combine these two functions, it means the output of one is going to be used as the input of the other one. What does that mean? Well, sometimes the thing is written in this following notation. Composition of f and g can be done one of two ways. One of them is the following: f circle g of x, or in more familiar notation, f of g of x. This notation implies that you take x, pass it to the first function g, take the output of that, and pass the output as an input of f. So in this case that I wrote here, output of g is input of f. So what does that really mean? Well, output of g means you take a g, plug the x in it, and you get 2x plus 1. So now, instead of g of x, you can write 2x plus 1. Next, that output is going to become input of f. To make that clear, let me go ahead and write the input of f in some other color. So here's the input of f. Just make it stand out loud and clear. So now we are going to take this one, this new input, 2x plus 1. So this purple color is going to sit for the blue one all over across the board, and we are going to get the following. So let me go ahead and write it. I take that and put it there. Maybe let me use the same color. It's 2x plus 1. So wherever you see that blue stuff, you have to replace it by this purple color. So it's going to be 2x plus 1, that's going to be squared. And then plus 3 times 2x plus 1. And then you have that 1 still being added. Well, if we could go ahead and get the answer simplified in some other fashion, we might continue the algebra. Usually we don't have that luxury unless the problem is very simple like these. For example, here you could square it and get, say, 4x squared plus 4x plus 1. That is coming from here. And then here is 6x plus 3. That's the contribution from here. And then you have 1. Then you can combine them and get 4x squared plus, say, 10x, and then, say, 5. So that's what's meant by the composition of function. And what we have in mind is that if I intend to do such a composition, how would I differentiate the final output? Well, in this case, you might say, well, go ahead and differentiate what you have in front of you. But as I said, it's quite rare that you can actually simplify this and write it in terms of other familiar functions. Most often, the problem does not yield to that simplification, like this cosine combined with x squared. There isn't any other format of writing it for us to go after that and try to differentiate that one. So we are really stuck with that or this. Most often there isn't anything else we could do to these functions, and we still want to differentiate them. Well, let me go ahead and now give you, after all this suspense, let me just tell you how to differentiate. So here's the mechanics of differentiating. Differentiating the composition of two functions. So suppose you have x as your input, you're passing it to g, you're taking this whole thing and you're passing it to f, and you want to take that whole composition and differentiate it. It turns out that you actually need to differentiate each of these two functions. So whatever function you see, you have to differentiate. So we are going to have f prime and g prime, and each function is going to be differentiated at its own input. The input of g was x. The input of f is all of this g of x. And then these two items are multiplied. Sometimes for talking about the situation, we refer to this g as the inside function or the interior function. And we refer to f as the exterior function or the outside function. So this one will be the exterior or the outside function. So we are going to calculate the derivative of the interior function. We are calculating the derivative of the exterior function, and each of them is going to be evaluated at its own input. So the interior function is evaluated at x, the exterior function is evaluated at the interior function. Now that is going to be perhaps still a bit abstract sounding, but let's go ahead and practice. Suppose I want to differentiate cosine of x squared. This whole thing is going to be differentiated. Now we need to recognize now who is the interior, who is the exterior function, or who is the inner and who is the outer function. That's another perhaps that is easier to talk about that way, so let me just write that one. Also inner function, and this one you might call it the outer function. Okay, here we have to detect that the inner function is our x squared. That's what is acting as an input of the next function. So whatever that is, it has to be differentiated. So we go ahead and differentiate that. It's become 2x. The outer function is cosine. That function has to be differentiated also. So we are going to have that one coming here as minus sine. The derivative of cosine is minus sine. Now the outer function was being evaluated at this inner function x squared. The derivative of it also is going to be evaluated at the same inner function. So I'm going to have sine of x squared. It's more customary to put the small items, more trivial items up front. So this is typically written as minus 2x times sine of x squared. Okay, let's go ahead and have more examples. So here we are going through a list of our examples. Example 1, example 2. Suppose let's take a simple one. Say sine of x cubed plus x. We want to differentiate this whole thing. Again, the idea is to differentiate the inner function. So I learned my lesson from that side. I'm going to go ahead and write the derivative up front. Derivative of this one is x cubed, x squared, 3x squared plus 1. Then I have to differentiate my exterior function. So that's going to be cosine of, cosine of what? Cosine of whatever we had first time around, x cubed plus x. Let's go take another one. Suppose I have exponential of x squared minus 2x plus 3. We want to differentiate this. Well, conventions in mathematics, so the way it is being written might come in the way of explanation right now. This is still a composition of two functions. What two functions are they? Well, the inner function is this x squared minus 2x plus 3. The outer function is exponential of x. We have combined these two. So if you want to differentiate it, this inner function, the derivative of that is 2x minus 2. The outer function is this exponential, which is going to be still x. The derivative of exponential is just itself, and whatever input you had, you still have it. Let's go take another one. So if we say tangent of, say, radical x plus x squared. I want to differentiate this whole thing. Okay, so gradually the problems become a bit more complicated, so we might want to do just one step at a time and not to compress too many things all at the same time. We have to worry about this inner function. I have to take, I was using green color for it. So here is my inner function. I have to differentiate it. Let me not put too much burden on myself and postpone it for next time around. Maybe radical x plus x squared has to be differentiated times a derivative of tangent. I don't need to wait for that. What's the derivative of tangent? That was secant squared. You remember? Secant square of what? Whatever we had first time around. Radical x plus x squared. Are we done? Well, not really, because we postponed a piece of the puzzle to the next round. So I have to take the derivative of radical x. You have seen this often enough for doing right away, or perhaps you want to write it in the exponent notation and do it like that. So maybe I write it on the side. How do you differentiate radical x? Let me write in different color. Radical x, you want to differentiate that. If you don't haven't memorized the formula yet, you write in exponent notation, then differentiating it 1/2 x to the power of 1/2 minus 1. That's going to be 1/2 of x to the power of minus 1/2. Writing it in nice fashion would be 1/2 radical x. Okay, it's a good thing to memorize. The derivative of radical x is 1/2 radical x. So I'm going to write 1/2 radical x. Derivative of x squared is just 2x. And then we have whatever else, secant square of whatever we had first time around. Now let's make sure we understand what secant square means. It doesn't mean you're squaring this. Let's write it out so that we are clear as to what we are doing here. 1/2 radical x plus 2x, and then this means that you apply the function secant to this input, and when you are all done, you find that number, whatever it is, and you square that. Has nothing to do with squaring this parentheses. Let's go ahead, take a few more examples. Problem 5. Example 5. Let's see what's a good example. Say secant of radical x plus 2. I want to differentiate this whole thing. So, by now maybe you want to pause this thing. You can go ahead, figure it out, and come back. So first step. Okay, I hope you went and paused, and this is after the pause. I have to take a derivative of radical x plus 2. So let me postpone that. Just to make the problem a bit more interesting, maybe let me put something here, say 3. Okay, so that's the inner function. It has to be differentiated. The outer function is secant. What was the derivative of secant? Derivative of secant, remember that was a function, secant tangent. Now, who is the input of these functions? We cannot just leave them hanging there without any input. The derivative has to be applied at some point. At what point is it going to be applied? Whatever you had here to begin with. So this is radical 3x plus 2, and again radical 3x plus 2. Okay, now what is left to do? We still are struggling on the first piece of this thing, which was radical 3x plus 2. We want to differentiate that. Well, that is actually another example of a chain rule. What are the two functions? One function is square root, and the other one is 3x plus 2. So if we had a word for square root, perhaps it would have been a little bit clearer as to what is happening here. So perhaps we go ahead, use a notation they use in computer science sometimes, or some programming languages. Instead of using that notation, I will use, say, square root like this. So suppose that just means take a square root of 3x plus 2. We are differentiating this. We are still not done with the first piece. Now, what is the derivative of this one? I have two components. One is, this is again the inside of that, the derivative of 3x plus 2. Well, that's easy. Derivative of 3x plus 2 is just 3. Now, what's the derivative of square root? Do you remember what the derivative was? We just did it a moment ago. Derivative of square root is 1 over 2 square root of whatever you started with. So derivative of square root is 1 over 2 square root of what? Well, whatever you had here, 3x plus 2. So this whole thing, if we write it in a more traditional notation in mathematics, they use that notation, 3 over 2 square root of 3x plus 2. Well, now this became a complicated example. Let's go back and write down what we have here. You remember, we start with secant of square root of 3x plus 2. So this is really a triple layer function, not just 2. Here is innermost function, and then we have the middle function, and then we have one outside function. There's really 3 layers heaped on top of each other. So we did one at a time. Take a radical square root of 3x plus 2. Differentiation of that is postponed to next step. Just differentiating the outer function. Secant, derivative of that is secant tangent. Those derivatives are going to look at the same input that the original function was looking at. Now for the next layer, radical 3x plus 2. What's the derivative of that? Here we say again, this is really a combination of two functions, square root and then 3x plus 2. Derivative of square root, we know that it is 1 over 2 square root, and that's going to be applied as the same input that it had here, Derivative of 3x plus 2 is just 3. So let's go ahead and rewrite this thing. We have a final answer for secant of square root of 3x plus 2. If this whole thing is to be differentiated, for this portion we had that answer, 3 over 2 radical 3x plus 2. And for the outermost function here, we had secant tangent, secant of the same thing, and the tangent of the same thing. Okay, maybe I pick a few more problems to do, perhaps with different emphasis. This was example number 5. Example number 6. Let's go to something easier. F of x, suppose I want to differentiate x cubed plus 7x plus 1 to the power of 10. Now we have seen this problem before in the previous lecture, but it is actually one of the more famous examples of applications of chain rule. We looked at it as a special case of product rule. Now it's going to be a celebrated case of the chain rule. Well, where are the functions? Where are those words that used to show up front? Again, we are victim of mathematical notation here. This power is actually a function. What function is that? It's a function of x, or your input raised to the power of 10. This is another function. This is your innermost function. That is, if you're dealing with this whole thing, you have to plug the x inside of this parentheses, innermost parentheses. After you are all done with that, then the second stage kicks in. Second stage is raising it to the power of 10. So if I want to differentiate this, I go in 2 stages. I say this is my interior function. I take the inner function and differentiate that. The derivative of that is just 3x squared plus 7. Where is the exterior function? Exterior function really this power, raising to power of 10. If I had x raised to power of 10, how would I differentiate that? So 10x to power of 9. Now my exterior function is this item is raising to power of 10. The derivative of it is going to be 10 what? 10. That power function has to be applied to the interior. So I write x cubed plus 7x plus 1. That is the value of the interior function. It has to be raised to power of 9. Now we abbreviate all of this and write it by the following formula. If I have any function like this raised to power of, if I have any function raised to power of n, and I want to differentiate that, I look at this as a 2-stage process, that I'm taking x, passing it to f, taking that whole thing, raising it to power of n, taking all of that and differentiating that. So I have an innermost function which is just this f. The derivative of that would be f prime. And then I have an outer function which is raising to power of n. The derivative of that is n raised to power of whatever raised to power of n minus 1. Now what's going to be the input? The input is the output of the previous step, which is just f of x. It's customary to write the answer like this: n up front, then f prime of x, then f, we write the exponent on top of the name of the function instead of all the way out. To make things short and compact, we use that notation. Let's see if we understood how to do this thing. So suppose I take the same example as I had here, x cubed plus 7x, example 7, x cubed plus 7x plus 1 raised to power of 10. Want to differentiate this whole thing. Take the exponent up front, write the derivative of the base, take the base and raise it to 1 less exponent than before. Okay, among all the applications of chain rule, this is the one you see most often, or the simplest case of all application of chain rule, and you want to be quick and accurate with that. Let's go ahead, apply this to another case. Suppose I ask you what is the derivative of 5th root of x to power of 2 minus 9x plus 1. I want to differentiate this. Best strategy is to write this in the power notation, that is x squared minus 9x plus 1 raised to power of 1/5. So I'm using power notation. Then I want to differentiate all of that. Well, what was our shortcut? The exponent comes up front. The derivative of the base, 2x minus 9, and the base raised to power of 1 less than the old exponent, which is 1/5 minus 1. Clean this up a bit. So 1/5 of 2x minus 9, x squared minus 9x plus 1 raised to power of minus 4/5. If you want to write it in the radical notation, you can just write it like this. This becomes 2x minus 9, 5 times radical. The index is 5. The power is 4. Power can be either inside or outside of the radical, either way. Okay, these were simple examples of chain rule. Let's go after some examples which are somewhat more complicated. Here, this was example 8. Suppose I want to differentiate sine to power of 10 of x squared plus x. This is really, again, a 3-layered function. Taking x and making this one out of it is the first layer. Who's the next layer? Who goes next? Of course, sine gets applied to that. Who's the last layer? Raising to power of 10. So maybe we go ahead and make it clear that you are taking x, making this out of it, then you take sine out of it, and the last item that kicks in is raising to power of 10, and then derivative comes in at the very last moment. When you have several layers of functions heaped on top of each other, when you want to differentiate, you go to the innermost. Here's derivative of x squared plus x, just 2x plus 1. Then derivative of sine is cosine. What is cosine going to look at? Cosine is going to look at whatever sine was looking at, x squared plus x. Okay, and then what is the last layer, or the outermost function? Outermost function here is power. What's the derivative of something raised to power of, say, 10? That's going to be that exponent 10 times the base that you had. The base is sine of x squared plus x. That base has to be raised to power of 1 less than the old exponent you had. That's 9. Again, it's customary to write small items up front, so 10 comes before this factor, or perhaps absorbed inside of it, and this becomes 10. 2x plus 1. So we have a progression from the small pieces to the largest piece. This is x. And for brevity, we put this exponent on top of the name of the function. So we have sine to power of 9 of x squared plus x. So when you have multi-layered functions and you differentiate it, it kind of foams up, kind of opens up, and suddenly becomes one of these sponges that they have it compressed, and you drop it in water and all of a sudden it just becomes a huge thing. Multi-layered functions, when you differentiate it, each of those pieces is going to give you one separate formula, and so the result is going to be a long function. So do not be surprised by that. That is quite common. So maybe it's a good time to just formalize this thing and see what is happening. Suppose I have x, passed it to some function, we call it g, and that one is passed again to some other function called f, and that one again is passed to third layer, and the third layer, typically they use the letter h here, but I'm afraid you are going to confuse it with the h we have used in the limits. So let's say k, some function. So I have a function k, function f, function g, and here is the input, innermost input, and the whole thing is to be differentiated. So could you pause for a moment and go and figure out how the right hand side is supposed to be written out, and come back and compare your answer against what I'm going to write here. So the way typically we write this thing, if we want to keep the small items up front, here, derivative of the innermost is g prime. Here's the middle guy, f prime. F prime of what? F prime of whatever f was looking at. F was looking at g of x. And then k prime. K prime of what? K prime of whatever k was looking at. So it's going to be f of g of x. So here are 3 layers. Special case of this, power of some function whose input also has been replaced by some other function. How you differentiate this? This is a special case of this previous one. Instead of k, we have a specific power application. Well, we know that this g prime comes in, and then you have the derivative of f to power of n. Derivative of f to power of n is going to be n f prime times f to power of n minus 1. Remember that derivative of something raised to power of n was the exponent, derivative of the base raised to 1 less than the old exponent. Who are f prime and f going to look at? Whatever f was looking at here. F prime is going to look at g of x, and f also is going to look at g of x. So this is getting a bit complicated, but standard issue that you have to deal with, and hopefully when you do these exercises this becomes second nature for you. Once again, look at the right hand side. We have 4 pieces, and inside of each of them we have things to watch out for, and on the left hand side we have something that looks quite compact. Let me take another example here. Suppose I have that was problem number 8. Here's problem number 9. Tangent to say power 5 of say cosine of, let's use the angle here, theta. We want to differentiate this. So again, this is a triple layer function. Derivative of cosine is going to be minus sine. I park the minus up front here, sine of theta. Tangent to power of 5, anything to power of 5 times the derivative of tangent. Derivative of tangent is what? Is secant. Just secant? No, secant square. Secant square of what? Secant square of whatever tangent was looking at. So that's cosine of theta times what else? What else is left? 1 less than the power we had here. So tangent to power 4 of cosine of theta. Okay, you got that? So innermost function here, derivative of cosine was sine, left the minus up front. Derivative of tangent to power of 5, that was the exponent. Derivative of the base, derivative of base like here, derivative of the base is secant squared, and then we reduce the exponent 1 notch. Who are these going to look at? Remember, secant was coming as a derivative of tangent, so whatever tangent was looking at, secant is going to look at the same thing, and this power comes from this tangent, so whatever that one was looking at, which was cosine of theta, this one looks at the same thing. So notice, do not get confused, this came from cosine of theta, so the argument of that is just theta. You'll see in the exercises even quadruple layered functions. The idea is the same, and you just have to approach it with care. Okay, let's see if we can go ahead and give an explanation for this. This is one of the cases where the formulas are a lot more complicated than the explanation. At least the simplified version of it, it's quite straightforward. It is the actual proof, the rigorous proof, that is a bit trickier. Okay, now we are going to go to geometric explanation. Okay, for the geometric explanation I need to go to 3 dimensions, and that is going to be a bit unsettling, but I hope that pictures come out nice so that you can grasp what is being explained. What I have in mind is to have a input x that is given to some function g, and the output we're going to call it, say, u, and take the u, give it to some function f, and the output is going to be, say, y. So here the example for what we're talking about, u could have been, say, 2x plus 1, and y could have been, say, u squared minus 3u plus 2, say. Now if I take this u, which is 2x plus 1, and I'll replace it here, I'm going to have my composition function. That y is directly being evaluated in terms of x. Here, if I want to write it, say, if I want to write y in terms of x instead of u, I have to replace whatever u is. So here, if I wanted to do the replacement, instead of u, I would have written 2x plus 1, and then 3 times 2x plus 1, and then a 2. Okay. I'm going to first take my functions to be super simple functions so that the picture is going to be clear, and then later on I'm going to say, regardless of what function you have, the properties will be exactly all the same. So here is my three-dimensional picture. So I make room here. So you have to kind of visualize this thing as a three-dimensional coordinate system. This would be like the corner of a room, and here are 3 walls here. So this is the floor, this is the back wall, this is the left wall, and I go ahead and call this x, call this u, call this y-axis. So if I want to investigate any of these in terms of any other one, I can just limit myself to the particular page or particular plane. So if I want to study x versus u or u versus x, I'm going to focus on this plane that is here. If I'm looking at y versus u, I'll be in the side plane. Y versus x, I intentionally put it the way you're accustomed to. Okay, I'm going to consider some a nice function here, something that would be easy to visualize, which would be a straight line. So here is a line in space. Visualizing it in 3 space is going to be a bit hard, but let's try. I take this, so imagine I have some curve sitting in the middle of a room. I can take the shadow of this curve on the XU plane. So suppose there is a light all the way up here, and the shadow is cast down on this page. And the second time around, I go ahead and cast a shadow of this thing on the YU plane. Let me go ahead and first draw my box so that everything matches nicely, hopefully. So this was the shadow that came all, straight down. So let's say the shadow on the YU plane is here. So what do you mean shadow on the YU plane? As if sun was here, or a source of light was far away on the right, and this would cast a shadow on the YU plane. So after all this effort, all I did was to draw a box. And once again, suppose the source of light is all the way at the end of this U axis, all the way at infinity. Then this purple line in space is going to have a shadow on the XY plane, and I'm going to go ahead and draw that in green again so that it stands apart from purple one in the middle of space. Okay, now I have these three green lines. Really, later on I'm interested in curves, but curves are going to just make the picture complicated to talk about. So a line is just as good as a curve. I ask, what are the slopes of these lines? Here I have three lines which are three shadows of the same entity. What are their slopes? How are those slopes connected to each other? Really, chain rule is about the connection of slopes of shadows of the same object on several planes. Okay, we are stuck against one thing. When you start your algebra classes, you always have x horizontal and y vertical, and a slope means rise over run, and things are rather clear cut. But here, what do we mean by slope? What is rise over run? So we have to just make that clear to ourselves. It's not a big deal. It just has to be very clear as to what we mean by slope. So suppose here, if I want to talk about slope of this line, I'm going to talk about it in terms of rise in U divided by run in X. Rise of U divided by run of X, or change in U divided by change in X. Instead of using these words rise and run, it's a bit more professional to use the word change. Change of U, we show it by delta U. Change in X, we show it by delta X. So we defined it this way. We had the option of defining it upside down as well, but here is how I took it so that everything matches later on. How about the slope of this one? Well, so let me go ahead, use the other terminology. I'm going to call it change. Again, we have an option of whose rise and whose run. After all, here it's not all that clear. Change in Y, perhaps it is clear. Change in Y divided by change in what? Remember, we are working in the U-Y page. So here's a change in U. For a certain amount of change in U, how much are our elevation going up? So that is going to be delta Y divided by delta X. Excuse me, I made the same mistake that I kept telling. This is delta U. Third round, who is the slope of this one? Well, this is the familiar X versus Y, and here the convention slope is change in Y divided by change in X. Let me give just some numbers so that we make sure we understood what these quantities are. Suppose this line that I drew and this box that I made out of it, let's assume that this is, say, up to here, say it is 3 units long up to here, and this is 5 units long up to here, and say this one is say 4. So the dimension of this box here is, this side is 3, 1, 2, 3, 4, 5, and this one is 1, 2, 3, 4. Let's go back and make sure we understood these things. What is the slope of this line by this notation? Pause for a moment, look at the picture. I'll be asking, what's the slope of each one of these things? Well, delta u for this line, the change in u, or the rise of u divided by run of x, is just 3/5. How about here? Rise in y versus the run in u is just 4/3. How about this one? Rise in y divided by run in x, that is 4/5. Well, what's the connection of this to these two? It's obvious that this delta u that is in the denominator is saying delta u that is on the numerator there. So if you multiply these two, these 3's cancel, and you get 4/5, which is just that 4/5. So if I want to write that observation here, I'll write it that delta y over delta x is same as delta y over delta u times delta u divided by delta x. It's just a matter of simplifying this fraction and getting that thing out of it. Well, you remember the slopes were precursors to our understanding of derivatives. This is really telling us what is the derivative of y with respect to x. So let's write it down. This is derivative of y with respect to, let me abbreviate, with respect to x like this, and excuse me, this is my hardware is breaking down, but anyway, delta y or delta u, this is derivative of y with respect to u, and who's this? This is derivative of u with respect to x. So we have 3 layers of items or commodities. X is influencing u, which is turning to influence y. And you want to get rid of the middleman and connect x to y. And you want to find out rate of change of y with respect to x. We are simply saying that you can create it out of 2 rounds of rates of changes. You have to simply multiply them because of simple fraction property. Really nothing else is involved here. So if you want to write derivative of y with respect to x, write it as derivative of y with respect to u times derivative of u with respect to x. Let's just go ahead and practice this thing. Suppose I start with x and I want to make a middleman u out of it. And here suppose my I make it by taking x cubed plus x plus, say, 5. and I have y that I'm making it out of u. Say it is u to the power of 10. I want to find out derivative of y with respect to x. After all, x changes makes u to change. When u changes, y will change. So I can find out how y depends on x. What is the sensitivity of y to x? This chain rule tells me take a derivative of y with respect to the next element of the chain. So take the derivative of y with respect to u times the derivative of u with respect to x. That is the chain rule. Now I go ahead and just do it. dy du, derivative of y with respect to u is just 10 u to power of 9. Derivative of u with respect to x is just 3x squared plus 1. We typically don't like to write our answers in several languages. We want to convert everything to just one language, one variable. So remember, u was x cubed, so I write 10. Instead of u, I write x cubed plus x plus 5 to power of 9 times 3x squared plus 1. Now, let's go ahead and take a second look at it. This u, if you want to get rid of the middleman here, you would write it as y is equal to, instead of u, you write all of that. It's x cubed plus x plus 5 to power of 10. This component of y, we were referring it to as the inner function. Inner function is just same as u. And this one, this activity, we were referring to it as the exterior function. And the rules that we have developed, all of them are just examples of this chain rule. And that is the main concept that is involved here. So chain rule, again, in short, chain rule means dy dx. So we are talking in the context that x is influencing u, who is influencing y. And I want to find out how does x influence y directly. I apply the chain rule, which means I take a derivative of each with respect to the next element of the chain. Just multiply all those derivatives. So that's what the chain rule is. Now, in this picture, if instead of a straight line I had a curve in space, I still can make these three shadows of it, and at each point of that shadow I can go ahead and try to find the slope of the tangent line. So there's a tangent line down here, a tangent line down here, a tangent line up there, and the slope of that tangent line is product of slope of the two tangent lines here, or the two shadows here. That's what this observation says. The fact that you have a curvature in space is not going to make any change in the reasoning that we are offering. It's going to be all the same. Now that is a geometrical or intuitive explanation of this thing. You can still come up with a little bit more refined, more algebraic proof of this. And let me just try, see if this next round of explanation, if it is going to help. Let's take a function and just go ahead and differentiate it and see if that helps. Suppose I take f of x is equal to, say, sine of x squared. I want to find f prime. Well, let's go back from the very first lecture in the course to start building from there. Derivative was a limit of something. Of what? I have to go ahead, take this function, change the input of it. Instead of x, supposed to use x plus h. figure out how much the function changed, divide by the change in the input, and let that change go to 0. The intention is to find that. We want to explain where do all the components come from. After all of these things that I have said, we know that f prime from the mechanical justification or mechanical description of the formula was the derivative of interior function 2x and then derivative of exterior function cosine times x squared. Our intention right now is to say why is that so. So we are going a little bit deeper. We talked about explaining it by geometry, a little bit from just algebra and no pictures here. Well, let's go ahead and open this thing up a little bit. I write limit of sine of, well, this is x squared plus 2hx plus h squared minus sine of x squared divided by h. Now I do the following. Just like those rationalization tricks and so on, I try to write down something in the denominator here that will match the numerator. That is, I'm going to write sine of x squared plus 2hx plus h squared minus sine of x squared I'm going to make another fraction and enter something in numerator and denominator that will cancel each other out. What's the item that I'm going to enter? The item that I'm going to enter is just the difference of these two inputs. That I'm going to write x squared plus 2hx plus h squared itself minus x squared, and then I'm going to copy exact same thing here, and this denominator that I had over there, I bring it down here. Now h is still going to 0. Now when h goes to 0, what happens to this? Same thing here and here. That's some small quantity, is that right? So let me just give it a name. Maybe that makes it a little bit clearer as to what it is. This is sine of x squared plus small quantity. Small quantity, what's a good name for a small quantity? Let's just call it, say S for a small quantity, minus sine of x squared divided by, well, remember these x squares and x squares cancel each other out, and all that we are left in the denominator is just that small quantity. We notice that when h goes to 0, this small quantity also goes to 0. Is that right? When h goes to 0, this thing is small, goes to 0. So instead of talking about h going to 0, I might say s is going to 0. And then this is a separate deal. I can take a limit of that separately. Limit of, remember, I can either simplify this by canceling x squares, or perhaps to keep the origin of what this one is, let me just go back to where it came from. This is really x plus h squared minus x squared over h. Here h is still going to 0. Okay, sine of, now do not get sidetracked by the appearance of this x squared. So long as this is same as that, we are okay. Sine of anything plus a small quantity minus sine of that thing divided by that small quantity. Where does that go to? What's the limit of this expression? Well, that is exactly the definition of derivative of sine. It's just that the point that it is applied at, instead of being x, is just x squared. Other than that, this is exactly the same as the definition of derivative of sine. Let me just remind you on the side. If I wanted to find out derivative of sine of x, what would I have done? I would have written sine of x plus h minus sine of x over h as h goes to 0. Now instead of h, I've written s. Instead of x, I have x squared. So the answer also is going to be, instead of x, I'll have x squared. So here I'll have sine of, so what is the derivative of sine of x? Derivative of sine of x would have been cosine of x. If instead of x I put x squared, answer also is going to have x squared in it. So this portion is going to give me cosine of x squared. This is a contribution from all of that. And this one is something that we have been working on quite often since the beginning of semester. This is derivative of x squared. Is that right? If I wanted to apply derivative of x squared by an example like that, that's exactly what I would have written. So this is just x squared being differentiated. So what do we have at the end? Derivative of x squared, which is 2x, times cosine of x squared. So let's just review again. We started differentiating sine of x squared. Out came derivative of the interior function, and then the exterior function differentiated and evaluated at the interior function. Okay, so that was a bit more limit style of the proof of the chain rule. Make sure you go ahead and do all the exercises of this section. You need to actually practice a lot more than what is assigned to become comfortable with this, because we are going to use this quite often. It's one of the very important formulas. It cannot be skipped. Okay, good luck and God bless.